Myself Sreevani, working as Assistant Professor in the Department of ECE in Institute of Aeronautical Engineering, Dundigal. We have discussed the first topic in electromagnetic waves and transmission lines as Coulomb's law in the first lecture, and in this lecture we'll continue with the Coulomb's law. Along with that, the electric field intensity, then different continuous charge distributions, and followed by some of the applications of electric field intensity. So in this lecture we'll learn three different topics. One is electric field intensity, then different continuous charge distributions, and followed by applications of electric field intensity. So let us see what do you mean by, first of all, electric field intensity. Then in order to evaluate all such applications and derivation part related to electric field intensity, we must remember first what do you mean by Coulomb's law that we have already discussed in the first lecture. So according to that, the force equation for Coulomb's law is given by F equal to Q1 Q2 by 4 pi epsilon naught R square into AR, where Q1 and Q2 are the 2 point charges and AR is said to be a unit vector in the direction of normal to the direction of the wave. And epsilon naught is the permittivity of the free space medium, and its value already we know that permittivity of free space medium. And as we know that its value is given by epsilon naught equal to 8.854 into 10 power minus 12, and the units for this is farad per meter. Now, what actually electric field intensity? The definition for electric field intensity. As we know that electric field intensity, it is also called as electric field strength. Generally, it is denoted with the notation called E. And according to that, we will define the electric field intensity or electric field strength may be as the force per unit charge when that particular element is placed in a field called electric field. Hence, according to that, the mathematical statement for that electric field intensity is given by E equal to limit Q tends to 0 F by Q, where F is considered as a Coulomb's force equation and Q be the charge of an electron. And Q can be measured in coulombs and force F can be measured in newtons. So according to that, the electric field intensity E or electric field strength E can be measured according to the definition as E equal to F by Q, where F can be measured in newtons and Q can be measured in coulombs. According to that, the unit for electric field intensity E is given by Newton per Coulomb, and it is also measured as volts per meter, the unit for electric field intensity. So as we know that the definition for electric field intensity or electric field strength may be defined is it is the force per unit charge when that particular element is placed in a field called electric field. Hence, E equal to limit Q tends to 0 and F by Q, or simply we'll consider its ratio as E equal to F by Q. Then, according to where F is said to be the Coulomb's force equation, and as we know that for a 2-point charges, for 2 stationary charges, the force equation is given by here Q1 Q2 by 4 pi epsilon naught R square into AR. Then the electric field intensity at a particular point R due to a point charge Q located at a certain distance called R dash, and it is obtained as is if E equal to F by Q, then if you substitute in place of F by the Coulomb's force equation as Q1 by 4 pi epsilon naught R square into AR, by 1 by q. So here we have two stationary charges we have considered here as Q1 and Q2. Then in order to simplify in the easy way, we just consider one of the charge which exerts on the force is given by here Q, and the first charge is we are assuming it as Q1. Then the electric field intensity or electric field strength E is given by F by Q. Then 1 by Q in place of F, if we substitute the Coulomb's force equation, then 1 by q into q1 by 4 pi epsilon naught r square into AR. Then if this q and this q gets cancelled, hence E equal to q1 by 4 pi epsilon naught r square into AR. So that is the general equation is given by here E equal to q by 4 pi epsilon naught r square into AR. Then if we find the distance of that, means where AR, as we know that the unit vector AR is defined as R by its magnitude, means where this R is said to be vector form and this modulus of R is denoted with magnitude of that vector. Then if R is the distance between, if we consider the point charges, the point charge Q is located at a particular position R and the Q1 is located at a particular position as R dash, then the distance R is given by R minus R dash by its magnitude as R minus R dash. Okay, then these two equations are, if you substituted here, then Q into R minus R dash by 4 pi epsilon naught into modulus of R minus R dash whole cube. Why it is whole cube means already if you observe in the denominator part of this q by 4 pi epsilon naught r square is there. Then if you substitute in place of this AR by r by modulus of r, then this becomes modulus of r whole cube. Then if you express this in terms of distance form, then q into r minus r dash by 4 pi epsilon naught into r minus r dash whole cube. So this is the generalized equation. If we have only 2 point charges, then Coulomb's law can be defined. Then from that Coulomb's law, if we substitute F by that Coulomb force equation, then generally this electric field intensity or electric field strength is given by Q by 4 pi epsilon naught r square into AR. Then instead of having only 1 or 2 point charges, if we have n number of point charges, and we want to locate all n number of point charges in n number of position vectors, then the statement is replaced as for n point charges, means let us consider all n point charges q1, q2, q3 and so on qn, and these are located at r1, r2, r3 and so on rn, means these are the point charges, and here r1 to rn are denoted with position vectors. Position vectors. So, and then electric field intensity at a particular position or point is obtained as, means previously we have evaluated the equation for electric field intensity if we have only one particular charge. Now it is replaced for n number of charges. Hence, that E equation to be obtained as here equal to E equal to Q1 into R minus R1 by 4 pi epsilon naught into modulus of R minus R1 whole cube plus Q2 into R minus R2 by 4 pi epsilon naught into modulus of R minus R2 whole cube plus and so on plus Qn into R minus Rn by 4 pi epsilon naught into R minus Rn whole cube. Or if we approximate all these equations with a discrete sum as 1 by 4 pi epsilon naught. 1 by 4 pi epsilon naught means if you observe the first term, second term and third term, if you consider for the nth term, the common term between all the terms is here 1 by 4 pi epsilon naught. Then if you consider it as common 1 by 4 pi epsilon naught as separately, then summation of k equal to 1 to n, then qk into r minus rk by modulus of r minus rk whole cube. So then if you expand this, if you want to expand this equation by substituting k equal to 1 to n numbers, then the equation remains the previous statement. So E equal to 1 by 4 pi epsilon naught. Then if we substitute k by first one, then q1 into r minus r1 by modulus of r minus r1 whole cube Then if you substitute k by 2, then q2 into r minus r2 by 4 pi epsilon naught into modulus of r minus r2 whole cube plus and so on nth terms. So this is the nth if you have n number of point charges and we want to locate n number of point charges with respect to position vectors, then the electric field intensity E can be collectively written as E equal to 1 by 4 pi epsilon naught summation of k equal to 1 to n qk into r minus rk by modulus of r minus rk whole cube. Okay. So till now we have discussed what do you mean by electric field intensity, then how we have substituted in place of that F by Coulomb's force equation, then we have considered the generalized equation for electric field intensity E as Q by 4 pi epsilon naught R square into AR, and if we substitute in place of R by their respective a vector as q into r minus r dash by 4 pi epsilon naught into r minus r dash whole cube. So this is for only if we have one number of only one point charge and we located that particular charge at a distance position vector as r, then this is the generalized equation. Then instead of having only two vectors, two charges, we have n number of charges and n number of position vectors, then generalized equation for the electric field intensity E is given by 1 by 4 pi epsilon naught summation of k equal to 1 to n qk into r minus rk by modulus of r minus rk whole cube. So how we want to find the magnitude of this one? Means suppose if we have one position vector as r, let it be r equal to, it is located at 1, 2, 3 and r dash is located at 2, 3, 4. Then how we'll find the distance between these two? Means first r minus r dash is equal to. So what is r here? 1, 2, 3 means these are the component values are given. Let it be ax, ay and az. Yes, here also ax, ay, az. Along with the unit vectors, we will write this the distance r minus r dash. Then it is given by 1 minus 2 into ax plus 2 minus 3 into ay plus 3 minus 4 into az. Then here 1 minus 2 as minus 1 into ax plus 2 minus 3 as minus 1 into ay plus 3 minus 4 as minus 1 into az. Then r minus r dash is equal to minus ax minus ay plus minus az. So this is the vector form. Then if you find its magnitude, then modulus of r minus r dash equal to. So how we are going to find the magnitude? Then r minus r dash is equal to whatever the magnitudes which are exist in this means minus 1, minus 1, minus 1. So if you find its magnitude means minus 1 square plus minus 1 square plus minus 1 square. Then it becomes minus 1 square as 1, then here also 1, then 1. Then it becomes root 3. So like this, we are going to find the distance between any two vectors as like this. So this is about electric field intensity. So till now we have learnt two fundamental topics in electromagnetic waves and transmission lines. One is Coulomb's law, which deals with the force, and second one is electric field intensity, as we know that a force per unit charge is given by electric field intensity, and it is also called as electric field strength. Generally, that E can be measured as according to the definition Newton per Coulomb, or in general we will measure it with respect to joules per meter. So now next one is electric fields due to continuous charge distributions. So till now we have considered only one particular charge, let it be plus q or minus q, and if we have n number of point charges, all are representing with q1, q2, q3 and so on qn, like that we will consider. Now if we have the same point charges moving in a particular direction, only one particular direction, means throughout the direction that q is uniformly distributed. And if you consider two directions, means if you close that line, then it becomes a surface, and throughout that surface the charge is uniformly distributed. Or if you close that, open surface is said to be surface charge density. If you close that surface, then it becomes volume. So throughout that volume, then the charge is uniformly distributed. Like this, we have considered three current charge distributions, three continuous charge distributions as rho L, rho S, and rho V, where rho is the charge density for line, for surface, for volume. So if you consider in this figure, the first one is denoted with plus Q, this dot, only one particular charge. That's why it is denoted with the dot, and we are representing the charge with plus Q. Then that is denoted with here plus Q. Generally, we know that the charge Q can be measured as in coulombs. The same point charge is moving in a line, hence the charge is said to be here line charge, and throughout this line the charge is uniformly distributed. So it is moving from one place to the another place. Hence we have to consider the density along a line or on a surface or in a volume. So along a line means we have to consider L stands for here line, and rho is the notation for density. So hence it is given by rho L means line charge density. And for the next case it is surface charge density. If you close this line, if you consider two directions, means throughout the surface the charge is uniformly distributed. Hence at density is given by rho S, and this is called surface charge density, and it can be measured as density means per unit area it occupying some area, hence per meter square, and surface charge, here also this charge can be measured as in coulombs. Hence the unit for surface charge density is given by here coulomb per meter square. Then if we close this surface, then it becomes volume charge. Volume charge means we have to consider three directions among, hence x direction, y direction, and z direction. So here individually we have considered either x direction or y direction or else z direction. For a surface we have to consider one plane, let it be xy plane or yz plane or zx plane. Or according to the constant planes we have to consider xy plane means z is a constant here, constant, and yz plane means here x is a constant. Zx plane means here we'll consider y constant. So like that, we two directions we have to consider here for the surface charge density. Then to measure this volume charge density, we have to consider three directions as x, y, and z. Hence, if you close that surface, open surface, then it becomes volume. So volume charge means three directions we have to consider, hence per meter cube. And charge can be measured in coulomb per meter cube, hence the notation for it is given by rho v. So generally this rho v can be measured in coulomb per meter cube. Hence the continuous charge densities are line charge density, surface charge density, and volume charge density. Respectively, those three are representing with rho L in coulomb per meter, rho S in coulomb per meter square, and rho V in coulomb per meter cube respectively. Right? So these are the three continuous charge distributions in electrostatic fields or exist. So now based upon these three, we will consider what actually the differential elements of charges and integral elements of the charges, along with that electric field intensity equations are also. So firstly, first one, the charge element dq and the total charge q due to these charge distributions are obtained as, firstly if you consider dq. So where d is the notation for differentiation and q is for charge. Differential element of charge is denoted with dq for a line, hence it is rho L into dl. Rho L is the notation for line charge density. dl means we have considered only one line along a line, hence it is a displacement length is given by rho L into dl. So differentiation elements means dq equal to rho L into dl. Then if you want to find from this differentiation element dq, then q, then we'll consider both sides integration. So firstly, dq equal to rho L into dl. Then if we find both sides integration, so integral dq equal to integral rho L dl. So here differentiation integration gets cancelled. Remaining element is obtained is here q, and q equal to integral rho L dl. So this is the notation which we have considered for the line. Hence, that integration we have to consider with respect to L, where L stands for line. So q equal to integral L rho L dl. Like this is for line charge. Next continuous charge distribution as here surface. Hence dq equal to rho s into ds. Then if you simplify that, q equal to integral s rho s ds. Previously it is for L, hence surface charge. And for volume, dq equal to rho v into dv, which is equal to, from this q equal to integral v rho v dv. This is for volume charge. So rho L is for line charge density, and rho s is for surface charge density, and rho v is for volume charge density. So these are the differential and integral components of respective charges for the continuous charge distributions. Then using this charge elements q for line, q for surface, and q for volume, then if you substitute all these three in electric field intensity equations, let us see what are the finalized equations for the electric field intensities due to line, surface, and volume respectively. Right? So by replacing the charge q with the charge elements as dq equal to rho L into dl, dq equal to rho s into ds, and dq equal to rho v into dv. So now by substituting all in place of q by, means previously what is that equation for q? dq equal to rho L into dl. From this q equal to integral L rho L into dl. Now if we substitute generalized equation for electric field intensity as we have just now we have discussed, that is E equal to q by 4 pi epsilon naught r square into AR. Then if you substitute in place of this q by for line integral L rho L dl, and the rest of all these are same except this q is replaced by this thing. Hence integral E equal to integral L rho L dl by 4 pi epsilon naught r square into AR, and this is for line charge. Okay. Then for the surface charge, same as we know that dq equal to rho L into dl. Similarly, dq equal to rho s into ds. Now same thing, if you want to find the normal element for this q, integral s rho s into ds. Again, if you substitute in place of q by this equation, then E equal to integral s rho s ds by 4 pi epsilon naught r square into AR. And this is for surface charge. And for the third one, for volume, E equal to again dq equal to rho v into dv. From this q equal to integral v rho v dv. And if you substitute in place of q by integral v rho v dv in this equation, then again this E is to be obtained as E equal to integral v rho v dv by 4 pi epsilon naught r square into AR. And this is for volume charge. So these are the three continuous charge distributions along with the charges, and we have learned the electric field intensities for the three types of continuous charge distributions as line charge, surface charge, and volume charge. Okay. And the next is the first application we'll learn with respect to this electric field intensity as line charge. So previously we have seen just now electric field intensity E due to line charge, and electric field intensity E due to surface charge, and electric field intensity E due to volume charge. So we'll consider individually with simple examples, and we are going to analyze how much electric field intensity is exists due to this line charge in E. So this we are going to learn in the next one. So first application of that electric field intensity is for line charge. Hence electric field intensity for a line charge we have considered. So a line charge, and here if you consider the simple figure, so this is the figure which we have considered for the evaluation of electric field intensity E due to a finite line charge and for an infinite line charge. So for a finite line charge means the length of the conductor or the distance we have considered is between two finite points. If it is extended for minus infinity region to plus infinite region, and here this distance is fine, we would like to find based upon the length of the finite length of the conductor. So for a finite length of the conductor, for an infinite length of the conductor, so we will consider one simple example. Based upon that, we are going to estimate the electric field intensity E due to line charge. So as we know that the equation for that is given by E equal to integral L rho L dl by 4 pi epsilon naught r square into AR. So in order to evaluate this electric field intensity E due to line charge, here 1 by 4 pi epsilon naught is a constant, and we are differentiating this, or we are integrating this with respect to the line, hence it is differential element is given by dl, and along the line means density is given by rho l, that is line charge density rho l, and AR be the unit vector representation AR. So in order to estimate all such, we have to find what actually how much line charge density is existing, and what is the displacement length of this particular line, and what actually in which direction it is to be varied. So these are all the components which we are going to evaluate from this basic figure. Then finally, and substitute all such unknown parameters are evaluated from this figure, need to substitute in this equation. Then we'll estimate how much is the electric field intensity is evaluated due to this line charge. Now we are going to learn. So here a line charge with uniform charge density rho L extending from A to B along the z-axis. So if you observe here, generally, as we know that the electromagnetic wave or electric fields or magnetic fields, electromagnetic fields are considered with respect to the 3D wave. Hence, we are considering here three directions image as x, y and z. Here, three are mutually orthogonal to each other. Orthogonal means the angle between any two axes, any two directions, if we consider, that is 90 degrees. Between x and y, between y and z, between z and x, means x and y are mutually orthogonal. Y and z are also mutually orthogonal. Similarly, z and x also mutually orthogonal. So generally, coordinate systems are orthogonal to orthogonal coordinate systems only we'll consider here. Hence, and here, if we observe this thick line which is placed between point A to point B, so that is the finite length of the conductor. Means we'll consider one conductor which is having the 2 points, finite length of the points are denoted with A and B. And this is placed along, if you observe in this figure, so this is the direction which is given by Z. So that finite length of the conductor is placed along the Z direction. That's why the line charge with uniform charge density rho L extending from A to B along the z-axis. So this finite length of the conductor we'll estimate first, then if it extended towards the minus infinity as A and towards the plus infinity as B, then how much is the electric field intensity, that also we'll analyze. And AB is the finite length of the conductor, and DL at this particular point means this is the point called source point. So 0, 0, z dash is called as source point, and from here x, y, z are denoted with field points. So what actually this source point and field point? And the field point means at this particular point we are going to estimate how much is the electric field exist. And the source point means how this is representing along with the origin. Hence, x coordinate variable as 0, y coordinate variable as 0, and z coordinate is only z dash. Why we have considered here z dash means in the axis purpose, directions purpose, we'll use general notations as x, y, and z. And in order to differentiate that, we'll consider here a small difference variable as called z dash. Right? So 0, 0, z dash is said to be source point, and the field point is given by here x, y, z. Right? So between the source point and field point, we are going to find out the distance between these two. Right? So to find the distance between the source point and field point, now what are the extra variables are also denoted from the figure. First we will see. So this is the rho, which is the distance from this point T to the field point, which we are going to evaluate electric field intensity E. So 0, 0, Z, and it is located at a T, and the field point E is located at x, y, z. And the distance is given by here rho, is the distance from T to this field point. And here if you observe, there are three angles are there. From T to B, the angle is measured as alpha 2. And from T to DL, that angle is given by here alpha. And from T to A, the angle which is measured as alpha 1. Right? The first angle is alpha 2. This is alpha 2. And the second one, from this T to this DL is alpha. Then from this T to this A is given by alpha 1. Right? So clearly observe first the angle which will measure from T to B is alpha 2. From T to this source point is alpha, and from T to this finite end A, the angle is measured is here alpha 1. What actually this alpha 1, alpha 2? We'll see in the analysis part. And the field point which we are going to measure is located at x, y, z. Right? So from this figure, we'll consider some of the assumptions. Now, those assumptions are to be substituted in electric field intensity E due to line charge. Okay. So here if you consider first equation for the charge dq equal to rho L into dl, which is equal to rho L into dz. Why? Because if you observe in the figure, that finite length of the conductor which is placed between from A to B, then this is located in which direction? Z direction. Hence, this displacement length dl is denoted in the direction of z. Hence, dq equal to rho L into dl is the general formula. And if you find the dl value from the figure, then dl is nothing but here dz. dl equal to dz. Hence, dq equal to rho L into dl, and which is equal to rho L into dz. Next, and the total charge means this is the differential equation. Then from the differential equation, if you find the integral component, then q equal to integral za to zb into rho L into dz. Why this is za and zb? Means this is the length which we'll find out based upon the length of this conductor, and it is being placed along the z-axis. Hence, q equal to integral za to zb rho L into dz. Okay. Then note that the field point that is located at x, y, z, and the source point is located at x dash, y dash, z dash. Now from the figure, what are the components of x dash and y dash? So these two are representing 0, 0, and z dash remains the same. Hence the source point is located at 0, 0, z dash, and the field point is located at x, y, z. Why we have considered these two means in the formula itself we are going to find the distance as r. So this is the distance from field point to the source point. That's why we are representing we'll particularly consider the field point and the source point. Right? So source point is derived from the origin, and the field point which we are going to evaluate. So these are the 2 points which we'll consider from the previous figure. Okay. So from this figure, we'll evaluate source point and the field points. So now from the figure, dl is equal to dz dash. But the finite length of this conductor is placed along the z, and the variable which we have considered in the source point case as z dash. Hence, the dl is equal to, previously we have considered here dl is equal to dz, that is nothing but here dz dash. Okay. Then now we'll find the distance first. Why? Because if you want to substitute all the assumptions which we'll evaluate from the figure, that is E equal to integral L rho L dl by 4 pi epsilon naught r square into AR. So to find here what is the rho L and what is dl and what is r, what actually this AR, we have to consider some of the points from the figure which we have considered. So here the distance r is find first. And then r is the distance from, what is this, x comma y comma z is called field point, and 0 comma 0 comma z dash is called the source point. So now we'll find the distance between these two, field point to the source point. Hence r equal to x comma y comma z minus x dash y dash z dash. And we know that from the line we have considered only one direction, means that two direction will be, means the length of the conductor is placed along the z. Hence we will consider x component and y components as 0 and the z component as z dash. Hence the distance between two. How we will find the distance between two? As we know that x1 minus x2 into ax plus y1 minus y2 into ay plus z1 minus z2 into az. So like that, if you find the distance, first one. So from these two, if you find x minus 0 into ax plus y minus 0 into ay plus z minus z dash into az. So here x component as x, y component as y, z as z. But in the source point, x component and y components are zeros and will have only z component. Then the distance between two are given by x minus 0 into ax plus y minus 0 into ay plus z minus z dash into az. Now x minus 0 into ax is nothing but xax, y minus 0 into ay as yay, and z minus z dash into az is the distance between field point to the source point, right? So now in order to analyze this electric field intensity E due to line charge, we must know what actually the dl, what actually this r, and the unit vector as AR, and the line charge density as rho L. So in order to simplify this in the easy way, we'll just transform all this xyz coordinates. What are all xyz coordinates? These are all called rectangular coordinate system variables. Generally these three are ranging from minus infinity is less than or equal to x comma y comma z is less than or equal to plus infinite. So infinitely varies means it is unable to, it is difficult to find some distance between these two. Hence in order to find the distance in simple way, we just convert this rectangular coordinate system variables into cylindrical coordinate system variables. Hence we know that the transformation of formulas and all, as we know that rho, see here x, y, z are called the rectangular coordinate system variables, where rho, phi, z are called cylindrical coordinate system variables. And we know the relation between this rectangular coordinate system variables and the cylindrical coordinate system variables. As we know that rho equal to root of x square plus y square, and phi equal to tan inverse of y by x, and z in Cartesian is nothing but z in cylindrical. So now based upon these three, we'll transform all these x, y, z dash into equivalent cylindrical coordinate system variables as r, means this is the magnitude form. Modulus of r equal to, where modulus, this r is stands for magnitude. Hence from this magnitude of this is given by root of x square plus y square plus z minus z dash whole square, right? So this is given by root of x square plus y square is nothing but here rho, and we just transform this xax plus yay by rho, and rho a rho plus, and the third quadrant as z minus z dash whole square into Az. Hence, if you transform this rectangular coordinate system variables, the distance into cylindrical coordinate system variables, hence r equal to rho a rho plus z minus z dash into Az. Okay. Now, from this, r equal to modulus of r whole square equal to. So, if you find the distance as here, root of x square plus y square plus z minus z dash whole square, then square root gets cancelled. Then here, r equal to rho square plus z minus z dash whole square. And we know that rho is under root of x square plus y square. We find its magnitude, modulus of rho square. So, rho square is nothing but root of x square plus y square whole square. Square root gets cancelled. Remaining is here x square plus y square only. Hence, that x square plus y square is replaced by here rho square, and z minus z dash whole square remains the same. So, r equal to rho square plus z minus z dash whole square. Then, in the equation itself, we'll have the two variables as AR and modulus of R whole square. To find that, we'll consider here AR by R square, which is equal to R by modulus of R. Means, as we know that unit vector definition, according to that, AR equal to R by its modulus of R. Already in the denominator, we have R square. Then if you add to that, then it becomes R whole cube. Hence, r by modulus of r whole cube equal to, what is r which is obtained from this? Then that is rho a rho plus z minus z dash into az. This is the equation. So that we have considered here by modulus of r whole cube, means magnitude form is given by here rho square plus z minus z dash whole square whole power 3 by 2. So modulus of r whole cube means this becomes cube root of term. Hence, that becomes whole power 3 by 2. So, rho in the denominator, rho square plus z minus z dash whole square whole power 3 by 2 is substituted in place of this modulus of r whole cube. Then, if you find from this, the electric field intensity E is equal to integral L rho L dl by 4 pi epsilon naught r square into AR. From the figure, dl we find that is dz dash, and mod AR by modulus of R square is nothing but this is the equation, and R also we know that. So substitute all those assumptions from the figure we have found is in this equation, then we'll get here E equal to rho L by 4 pi epsilon naught treated to be as constants, hence we'll separate those variables. So rho L by 4 pi epsilon naught, and we are integrating with respect to line, hence integral L. And we substitute in place of dl by AR by R square, then it becomes rho a rho plus z minus z dash into AZ by rho square plus z minus z dash whole square whole power 3 by 2 into dz dash. This dz dash is nothing but dl. Okay. Now still if we want to simplify this one in easy way, we just evaluate this one. So to evaluate the above equation, so it looks like somewhat complex equation. To simplify it in the easy way, we just consider some of the angles which we have considered from the figure. So to evaluate this equation, we define alpha, alpha 1 and alpha 2, which are making angles in the electric field intensity E due to line charge from the figure. So R equal to, as we know that previously what we have considered for R equal to rho a rho plus z minus z dash into Az. Then if you find its magnitude, rho square plus z minus z dash whole square. Hence from that, R equal to rho square plus z minus z dash whole square whole power 1 by 2, which is equal to rho secant alpha. So how we'll find this one means, so consider here this is the figure. Now, so R is the distance between from the source point to the field point, and here then if you find the angle as from means from T to this source point dl, the angle which is measured as alpha, right? So this is the distance which is given by R, and here is the distance as z dash, and it is varies from z to z dash, and from T to this field point E, we'll consider the distance as rho, right? So from that, so secant alpha. So this is the triangle which we have considered, right? So this is the R and this is the rho and this is Z to Z dash, this one. So if you find here secant alpha. Secant alpha means it is the reciprocal term to the cosine alpha, hence it is secant alpha. For cosine it is adjacent side by hypotenuse, for secant it is hypotenuse by adjacent side, hence R by rho. From that, R is equal to rho into secant alpha from this figure. So the same thing we'll substitute here in place, hence R equal to rho into secant alpha from the figure. Now, if we simplify this equation, then rho square plus z minus z dash whole square equal to, means to get this one, already in the left hand side we'll have under root of term, then to cancel that square root we'll consider both sides square on both sides, then square root this cancel, and this becomes RHS part becomes rho square secant square alpha. Then separate the rho square terms and z terms, hence z minus z dash whole square equal to rho square secant square alpha, and if you take this rho square into this side, then it becomes minus rho square. Then if you take here a rho square as common, secant square alpha minus 1, right? So rho square into secant square alpha minus 1, secant square theta minus 1 is the formula for tan square alpha. Then z minus z dash whole square equal to, here z minus z dash whole square equal to rho square into tan square alpha. Why? Because for the formula here, secant square theta minus 1 as the formula tan square theta. Hence, we substitute in place of that, then it becomes rho square tan square alpha. And from this, z minus z dash is equal to rho into tan alpha, right? So, z minus z dash is equal to rho into tan alpha. Now, if you simplify this one, see, if you consider here z and z dash, which is the variable one, z dash only. Why? Because here z can be treated as a direction, hence we'll just consider it as a scalar. Hence, this differentiation variable as we have considered here z dash. Hence, dz dash is equal to, means minus dz dash is equal to rho tan alpha into d alpha. Means for this differentiation is given by minus rho secant square alpha. Rho is a constant. If you differentiate this one, the formula is minus secant square alpha with respect to alpha. Hence, dz dash is equal to, take this minus into this side, then dz dash is equal to minus rho secant square alpha into d alpha. Now, if you substitute, means previously this is the equation. In this, all the variables are replaced by whatever we have considered the angles in place of z's and all. So now, E equal to minus rho L by 4 pi epsilon naught, and integration we have considered with respect to the line, hence it is integral L rho A rho tan alpha Az by rho cube secant cube alpha into rho secant square alpha d alpha. So how it has come means, see here z minus z dash is given by, from the figure z minus z dash is here rho tan alpha, and dz dash is minus rho secant square alpha d alpha. Then if you substitute in place of z minus z dash by rho tan alpha and dz dash by minus rho secant square alpha d alpha in the above equation, then this is minus rho L by 4 pi epsilon naught rho integral L rho A rho, then rho tan alpha Az by rho cube secant cube alpha into rho secant square alpha d alpha. So this rho and this rho is, if you take as common, then rho into this rho becomes rho square, and in the denominator we have a rho cube, then rho square rho cube gets cancelled, and secant square alpha, the secant cube alpha gets cancelled. Then remaining is given by here E equal to minus rho L by 4 pi epsilon naught rho, and we are integrating this with respect to L, then integral L A rho plus tan alpha into Az by, and here rho as a constant again, rho L by 4 pi epsilon naught rho, and integral L A rho plus tan alpha Az by secant alpha into d alpha. Okay. So again, if you express this in terms of tan, means as we know that the formula for tan alpha is sin alpha by cos alpha, and for secant alpha it is 1 by cos alpha. Then all simplifications, if you substitute here, then a rho plus sin alpha by cos alpha into az by secant alpha means 1 by cos alpha. Then minus rho L by 4 pi epsilon naught rho integral L a rho means if you take here LCM, then a rho into cos alpha plus sin alpha into az by secant alpha into cos alpha into d alpha. So 2 are reciprocal, hence 2 gets cancelled. Then E equal to minus rho L by 4 pi epsilon naught rho integral L a rho cos alpha plus sin alpha into az into d alpha. So this is the equation for the finite length of the conductor case. Means we find that L length will be from the figure starting from the figure, it is the line which is located from A to B, finite length of the conductor. Hence the angles which are measured is here, from A is alpha 1, from B it is alpha 2. Hence the length will be ranging from here alpha 1 to alpha 2. Hence minus rho L by 4 pi epsilon naught rho integral L means we have to define that length is between from alpha 1 to alpha 2 rho secant square alpha a rho cos alpha, then cos alpha plus sin alpha is by rho square secant square alpha d alpha. So if you simplify the entire thing, then a rho cos alpha plus sin alpha into az d alpha. Now if you integrate and if you substitute the limits, then E equal to rho L by 4 pi epsilon naught rho, you take this inside, then a rho is a constant. Then if you are integrating with respect to cos and integrating with respect to sin with alpha, so integration of cos becomes sin, and for in place of alpha, if you substitute limits as alpha 1 and alpha 2, then minus of sin alpha 2 minus of sin alpha 1 into a rho plus. And for this integration of sin is minus cos, then if you substitute limits, then this minus and this minus becomes plus, hence cos alpha 2 minus cos alpha 1 into az. So this is the case we have considered for the finite length of the conductor we have placed along the z-axis, right? So if you want to extend that finite length to be an infinite length, hence as a special case we have considered for an infinite line charge, means that B is to be extended till plus infinity and A is to be extended till minus infinity. So then alpha 1 and alpha 2 may be defined as alpha 1 equal to pi by 2 and alpha 2 equal to minus pi by 2. Hence, if we substitute in place of alpha 1 by pi by 2 and alpha 2 by minus pi by 2, in this finite length of the conductor case, obtained equation for electric field intensity, then E becomes E equal to, so alpha 2 by minus pi by 2, alpha 1 by pi by 2. Like that, if you evaluate, the first two terms becomes 1 and 1, and cos 90 becomes zeros, hence we can neglect this one and we'll consider only a rho component. Hence E equal to, so already it is there, 4 is there in the denominator, then nu is to 2 is obtained in the from the numerator, then 2, this 2 gets cancelled, remaining is 2, then E equal to rho L by 2 pi epsilon naught rho into a rho is the generalized equation for the electric field intensity E due to an infinite length of the conductor's case. Okay, so E equal to rho L by 2 pi epsilon naught rho into a rho. E can be measured is here volts per meter, and rho L is the line charge density and it is measured in Coulomb per meter, and 2 pi epsilon naught, where epsilon naught is said to be permittivity of the free space medium and rho is the radius or from the length of the conductor, right? So in general, if you consider it as rho direction, then it will be expressed in terms of rho. Otherwise, if it is expressed along the phi direction or else along the z direction, whatever the coordinate system variables, if you consider, along with that, we are supposed to express the unit vector direction in that particular coordinate system. So here we are evaluating with respect to rho, hence E is equal to rho L by 2 pi epsilon naught rho into aero. Okay, so in this class, what we have learned is our definition of electric field intensity. As we know that electric field intensity is also called as electric field strength, and it is measured is force per unit charge when it is placed in an electric field E. So E equal to F by Q. As we know that the force equation from the Coulomb's law, and if you substitute in place of F by that, then E equal to generalized equation for the 2-point charges we have learned. And instead of having 2-point charges, if we have n number of point charges and we want to locate all n number of point charges in n number of position vectors, we have evaluated approximate equation for the n number of point charges case of electric field intensity. Then we have discussed 3 continuous charge distributions of electric field intensity as rho L, rho S and rho V. And generally these 3 are the charge densities, and these are measured with respect to Coulomb along a line per meter. For a surface, Coulomb per meter square. For a volume, it is Coulomb per meter square, meter cube. So here line means we have to consider only either of the directions of 3, either x or y or z, only one direction. For the surface charge, we have to consider planes like xy or yz or zx. And for volume, it is 3 directions we need to consider as xyz directions. Okay, so one of the application of electric field intensity as line charge we have evaluated. In this case, 2 different ways we'll analyze. For the first case, it is for a finite line of length of the conductor, and for an infinite line of the conductor. So for an infinite length of the conductor, electric field intensity E is obtained as E equal to rho L by 2 pi epsilon naught rho into aero. Right? In the next lecture, we are going to learn the next application of electric field intensity as surface charge. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.